and welcome to a lecture on Galerkin method. I hope you all have gone through the derivations that I have sent earlier. From the derivations you all have learned that this equation here to the right hand corner, this is the governing equation for any bar element which is subjected to a uniformly distributed force Q naught and or a concentrated load or any combined load. Okay, so this equation can be used if you have Q naught or P or combination of Q naught and P. Let us start solving our first problem. You are given a bar element which is fixed on one end and free on the other end as shown here. So this is the x direction. This is the length of the bar, capital L. It is subjected to a uniformly distributed force Q naught per unit length. The properties of it are E is the Young's modulus and capital A is the cross-sectional area. In this problem, you have to determine the expression for displacement using the Galerkin method. Now let U be the axial displacement at any point x. The governing differential equation of the bar subjected to only distributed axial load Q naught is given by the same equation we have written above. Applying the boundary conditions, since the left hand side is fixed, we know that at x equals to 0, the displacement at 0 will be 0. Similarly, at x equal to L, it is a free end. Okay, so at the free end we will have there will be no slope at that end because it is free end, or we can say dou u L by dou x, taking EA on the right hand side. Okay, this also indicates dou u by dou x. If you remember from the first principles, dou u by dou x is also the strain. Okay, so at the free end there is no strain. Now let us assume displacement function in terms of polynomial u of x equals to a0 plus a1x plus a2 x square. This is the same way we do it for Rayleigh-Ritz method. Okay, so a0, a1 and a2 are constants which have to be determined. Now when we use the first boundary condition, this one, boundary condition 1, we get a0 equals to 0, and let us label this equation as equation 1, and differentiating equation 1 with respect to x and apply the second boundary condition. So I'll say boundary condition 2, we will get a1 equals to minus 2a2 n. Now substituting the values of a0 and a1, in equation 1 we get u of x equals to a2 into x square minus 2 lx. Now this equation, let us call it 2. It satisfies the boundary condition and it contains one constant a2. Okay, so first we had three constants a0, a1, a2. Now we have only one constant a2, which has to be determined using Galerkin method. Now we know in Galerkin method we are supposed to find out, assume an equation of this form: phi 0 plus a1 phi 1 plus a2 phi 2 plus a3 phi 3 and so on. What we have to do here is, we know that phi 0, phi 1, phi 2 and so on are trial functions. Okay, phi 0, phi 1, etc. These are called as the trial functions. Now phi 0 is to be mapped with a0. Is there a a0 term in this? There is no a0 term. So we say phi 0 equals to 0. So we are comparing these two equations, one which we have in x and one which we have in phi. So phi 1, again there is no, phi 1 has to be mapped with a1 in equation 2. There is no a1 term here, so phi 1 is also 0. Next, phi 2 is to be mapped with the term a2 in equation number 2. So what is the coefficient of equation of a2 in equation 2? It is x square minus 2lx. Okay, so phi 0 is 0 here because there is no a0 term in equation 2. So there is no coefficient which a0 has. Similarly, phi 1 is again 0 because there is no a1 in equation 2, and phi 2 equals to x square minus 2lx because the coefficient, see, this is how it is to be mapped. Okay, supposing this equation u of x, say, was just an example 2a0 plus 3x a1 plus x square a2, and the Galerkin equation is phi 0 plus a1 phi 1 plus a2 phi 2. Okay, so here phi 0 would be 2, phi 1 will be equal to 3x and phi 2 will be equal to x square. Okay, so the coefficients of a0, a1 and a2 are equal to phi 0, phi 1 and phi 2 respectively. Okay, so moving on with this problem. So we have the equation u of x equals to a2 into phi 2. In equation 2, I am replacing this term by phi 2. So for determination of a2 using Galerkin method, the weight function w2 is to be taken same as the trial function phi 2. Okay, the weight function w2 is to be taken same as the trial function phi 2. Only one constant is unknown, and hence one weight function is sufficient to get one equation by substituting the weight function into the equation and solve for a2. That is, w2 is the weight function which is equal to the trial function phi 2. The trial function phi 2 is equal to x square minus 2lx. In Galerkin method, use the weighted residual method, in which the integral of w2 into the residual Rd dx has to be equal to 0. Okay, if you remember the derivation, you go through the derivation that was sent to you. It was integral v w I r d dv equals to 0 for I equals to 1, 2 and n, where wi was a weight function. So this is the same thing that we are applying here. Now since this is a bar element, this is going to be dx and not dv. Okay, and I here is 2 because we are talking about the weighted function, the 2. Okay, so the weight function 2, that is why we have here w2 rd dx has to be 0 over the length 0 to L. Okay, now as I said, this is the residual, okay, which is given by let us substitute for u in this equation. We get, after differentiating this twice, if you differentiate first time, you will get 2x minus 2l. If you differentiate another time, you will get just 2. So we have Rd equals to 2EA into A2 plus Q naught. Let me call this equation 3, and now we have the value of Rd with us. So I am going to substitute this value of W2 and Rd in equation 3. We get 0 to L, and I know W2 is x square minus 2x, Rd is has to be equal to 0. When I open this brackets and multiply, I should get something like this. After integrating and applying the limits, I will get an equation of this form, and this gives me A2 equals to minus Q naught upon 2EA. Now substituting for the value of A2 in equation 2, we obtain the displacement at any position x as lx minus x squared. So this is what was asked. We were asked to obtain the displacement of a bar element at any point x, and this is what we arrive at. Thank you.